Okay, so let's start writing our own custom little OS or bootloader to target VirtualBox. Let's go. So I'm going to make a directory for the project. I'm going to call it vbox underscore exploit. I'm going to cargo init in. And we're going to build this as a x86-64 UEFI target. And make sure I have rust up target add x86-64 unknown UEFI. I already have that. Cool. Now in my project folder, I'm going to create a .cargo file, .cargo folder. And in that .cargo folder, I'm going to have a config.toml. And I'm doing this so that I can set the default build target to be this x86-64 unknown UEFI target. Cool. Now that that's there, I can open CLion, which is just the IDE I'm going to use. Okay. Now let's start coding. I'll just zoom in a little bit to make it easier to see. Now, this is a UEFI target, so I'm not going to have the standard library, and I'm not going to have a main. When you're building a UEFI target, your main has to be called EFI underscore main, and it's going to be an extern CFN function, and it's going to take two parameters. It's going to take a image handle, which I'm just going to say is a usize or the size of a pointer, and a system table. And I'm going to say we don't return. Not only that, but this extern C function has to be exported and it has to really be EFI main. The name cannot be mangled. So I'm going to do no mangle. Now this should compile. It can't compile because I need a panic handler. Why? We're not using any standard libraries. So if we do something in our code that panics in Rust, it needs to be a function that handles that panic. Let me fix this quickly. Okay. So let's create the panic handler. This is going to be a function called panic that takes a parameter, which is Rust panic info. And then normally here you could do something like print the panic or something, but we don't have any print function set up or anything. So I'm actually not going to have this loop I'm going to have this loop at the end, but I'm going to actually use an unsafe block to call ASM UD2. And this is going to be call arc ASM. Cool. Why UD2? What I want to happen when my code panics at the moment is I want the VM to crash. So this is going to execute the UD2 instruction, which is going to raise an interrupt or a fault. And we don't have any fault handlers set up. It's going to double fault, then triple fault. And when a triple fault occurs, most hypervisors will just terminate the VM. Sometimes they reboot the VM, but most hypervisors will terminate the VM. So in this case, when a panic happens, this UD2 should cause the VM to terminate. If it for some reason it doesn't, then it's just going to loop forever. Now this should build. Yep, it built. If I go into target, x86 unknown UEFI debug, we have this vbox exploit.efi file. This is our bootloader, our UEFI bootloader that we can run in VirtualBox, and it'll run our own little OS. So this isn't meant to be a course on writing hypervisors or dealing with UEFI and things like that, or writing custom kernels. So there may be parts of UEFI that I kind of skim over, but UEFI is documented. If I search for, do I have a browser open? Yeah. UEFI specification. There's this specifications, and there is actually here a UEFI specification version, whatever, based on the latest one. And the specification, well, actually, here you go, 2.10, actually. You can download it in PDF, you can view it in the browser. And if I search here for EFI main, for example, actually, I'm going to download the PDF, open the PDF, and I should be able to search here for an EFI main, or just main. Okay, I would have expected there to be an EFI main, but that's fine. Um, if I search for entry, it should show what the entry point should be. UEFI image entry point. So this is our EFI main, right? Our EFI image entry point. This is the main entry point for UEFI image. It takes a EFI handle called an image handle and an EFI system table called which is a pointer to a system table. So we have the system table as our second parameter here. It's a pointer, so I just did usize to make it the size of a pointer. And the first one is an EFI handle. What is an EFI handle? I want to know what a EFI handle is. Is it going to tell me? Okay, EFI handle is defined as a void pointer. So it's a pointer as well. So usize works for that handle as well. So really, a lot of what I'm doing when I'm working with UEFI here is just based on the specification and working with it. Right now, for example, there is no way to do heap allocations. I can do stack allocations, but I can't do heap allocations. Because in order to do a heap allocation, I need to interact with something, some external API that can give me memory. And in this case, since we haven't exited boot services, that'd be using the allocation routines exposed by the system table. But I don't need to get into that for now, because what we're doing is pretty simple. Where's my steps? Here we go. I need to, well, first of all, let's define some of the vulnerable ports. Well, what am I working with? I'm working with port 430 and 433. They're the two ones that I'm doing. So 430 and 433. And 430 is used to initialize and do writes. 433 is used for a few other things. I'd like to use it as a constant. So let's do const vuln port u16 equals to 430. Let's do const 433 is used as a reset port. Although I'd want it to be within that range. Struct IO port, base is a U16. base is a U16. Max is also a U16. And then let's do an impl on this, where I have a get function on self, get offset on self, where it returns a U16, get port by offset on U16. It also takes an offset, which is a U16, and it does something like let do port equals to self.base plus offset, and then assert. I could do error handling here, but I'm clearly not doing error handling. I'm just going to make it an assert instead. And then finally here, new port is returned. Okay, so and let's make that a pub fn or pub create fn. So what I'm doing here, right, is when you construct a port, it's going to have a base and a max. So for example, the one we've been looking at, this vulnerable port that has a base of 430, its max is 434. So I'm going to construct the IO port struct with 430 as the base and 434 as the max. Now, when you want to get an offset to it, just like how we work with offset 3, offset 0, stuff like that, you're going to use this get port by offset function, and you pass through the offset, and it applies the offset to whatever the base is. And as long as that does not exceed the max value, you get it returned. If it does exceed the max value, something went wrong, and this assert's going to be hit, and it's actually going to panic with this message. Ideally, you do like error handling and things like that, but I don't think we need to flesh out this Rust code so thoroughly for just this simple POC, right? Even this can be a bit much for just this basic POC, but I'm going to do it this way anyway. All right. So first thing I'm going to do is I'm going to construct that structure. I'm going to have a const. Wait, did I do a const already? No. Vuln port is 430. And then const vuln port max U16 equals to 0x434. Let's vuln port equals to IO port, where base is vuln port and max is vuln port max. Okay. Now, what do I need to do? Step one. Step one is, wait, actually, step one is targeting out against port 430. And that was the reset, right? The targeting out against port 430 was during that reset operation. So let's do that reset operation. Let's actually have another struct. Skizzy port that has a base U16, a max U16, and there's an FN. No, we'll do an impl skizzy port, pub create FN init, which takes a base U16 and a max U16 and returns a self. And what was I thinking here? Skizzy port is essentially going to be an IO port, so actually this just needs to be a port IO port, and then this just creates a Skizzy port with a port value is here. And that can just be set to there. Okay. So here, Vaughan port is not going to be an IO port. It's going to be a SCSI port. I'm actually calling SCSI port init with Vaughan port and Vaughan port max. Okay, so I'm specifically getting a SCSI port. Why? IO port provides the base structures, the base and the max for the ports, and some of the generic port operations, such as getting port by offset. But some of the things I want to do, such as calling an out against port 430, which is actually corresponding to that SCSI reset function here, right? Because SCSI reset can be hit on case 3 here on the write register. So when you do a write register with case 3, sorry, it's not this first part. It's this number 1 here. This step 1 is an outright port 433. That's this case 3 VBox SCSI reset. So instead of just doing an outright to port 433, I can actually define this SCSI port structure, and that has init, which gets a handle to itself based on base and max. In fact, it doesn't even need to take base and max if they're hard-coded. If they're hard-coded, which in this case they are, it can take nothing, and it can return Vaughan port and Vaughan port max, and this is the base, and this is the max. And these constants can actually be in the function itself. And now here, when I do init, I don't need to pass anything. Okay. So now to get a SCSI port, I just call SCSI port init. SCSI port init knows the constant for the ports and the port max, and it creates itself with the port and port max and returns that out. Now that I have that, I need to do a reset. So I can do, or maybe I can just do exploit Vaughan port and loop. This exploit function takes the SCSI port that's been initialized, and it's going to do an exploit. It's going to do the exploit for us. Let's do fn exploit. It takes the port, which is, it's going to take a SCSI port, which is the SCSI port structure, and that's it. What's it going to do? First, it needs to do the reset operation, right? And actually, let me make this a mutable Vaughan port. And this is going to have a reference to it. This is going to be a mutable reference to SCSI port. So I'm going to do SCSI underscore port dot reset. Right? Because the step 1 we need to do is this outright, which is this SCSI reset command. The first thing we're going to do is implement the reset function on the SCSI port to satisfy the first thing we need to do. Let's implement reset. SCSI port. Now, ideally, these would again split into different files, but it doesn't matter for this POC. We're going to have a new function. Hub create fn reset. Going to take a mutable self. What is it going to do? It's going to use I want to create a new Rust file with CPU. And I'm going to have fn alt b. This is going to be inline issues the alt x86 instruction with the provided port and value. Takes a port. Yep, we have to import this. Takes the port, takes the value, does alt dx al. Dx is the port, al is the value, and done. Right. And you know what? That's a pub FN. In main here, reset reset is going to um we get a reset. We're going to do outright here. VBox gives you reset. Let me remind myself, does it actually need any specific value? No, it doesn't. Where does F everything come from? In the case 3. Oh, it's always true. Okay, so that's fine. So I can set it with any value. So, and it's going to be port 433, so offset 3. So let port equals to self.port.get port by offset 0x3. And then it's going to use outb. It's going to use port. Sorry. This is port, and value is going to be hard coded as 0. Done. So we have a reset function. It gets the port by applying the offset 3 to the current base, and then puts that as the port, and the value is 0, and that does reset. Cool. So reset's done. What's the next stage of the exploit? The next stage of the exploit is these multiple writes to port 430. And part of it is to set the buffer. In fact, I think initially it's to, well, let me see. Some part of it is to set a buffer. Let me see what the other parts were. This goes to VBox Skizzy, right? So we wanted to write at here with so from stage 2, we wanted to write it with value 0, which sets the target device. So here I can just have a function up here, pub create fn initialize device. It takes a mutable self. It's going to take a target device. Well, actually, I don't need to do that. I can hard code that. It's going to initialize it to device. It's going to set a buffer. It's going to be initialized device. It's going to take self, and then it's going to take a buff size, which is going to be a U32. Okay. Initialize device is going to do a reset, self.reset. So in here, I'm actually not going to do reset. I'm going to do dot initialize device, and it's going to take a buff size. I'm going to say let buff size equals to 10, like I said, right? And this is a U32. And I'm going to pass through buff size here. I actually don't need that there. Initialize device is going to call self.reset. Now, after that's been reset, the next stage, the next part is to set the target device to 0. So fn set target device at mute self device val u8, and it's going to do port 430, so it doesn't need to apply any offset. You can do outb self.port.base, and the value is going to be device val. Here we're going to do self.set target device to 0. Now the next part is to set the state to either txdir from device or txdir to device. For this exploit, it's going to be fn. Actually, this all has to be in order. So you know what? I'm not going to bother doing any of this because in order to do that properly, I need to manage the state of the skizzy. just like the state is managed here with enum state, I need to have like an enum that matches those states and then have the functions only callable from the device when it's in that state. But the aim of this isn't to write a actual proper like skizzy driver. It's just to trigger the vulnerability. So I'm going to keep it simple just for that fact. If I was writing an actual skizzy driver, it'd be a little bit different, but in this case, it's not. So let's do that step 2, which is I'll comment it though. Reset the device to set the enum state to the required initial state. Set the target device to some value to proceed further. Unsafe. CPU LB. Port is self.port.base. Value is just 0, which is step 2. Step 3, we set it to 1 in order to hit tx02 device. And tx02 device is going to be a constant here. Const tx02 device u8 equals to 1. Set the tx02 to device as required for the exploit, which is another unsafe block where we're going to be targeting port 430 again, the self.port.base, and with tx02 device. Oh, actually, I don't need unsafe at all because the CPU command is actually not marked as unsafe, even though it should be, because the function itself is unsafe. It isn't providing the guarantees. So the unsafe shouldn't be a block in here. It should actually be applied to the function itself. But again, they're things that I just really shouldn't care about for a POC. What's next? Now I need to write the buffer size. Okay. So, since it's using bits 0 to 19, I should make sure that the buffer size actually fits within that and it's not actually larger. But I don't care at this point. Let's just follow along here. Let buff size 1 or h equals to buff size shifted right by 12, ended with 0xf0. Buff underscore size. Let me remove that underscore. That's buff size h. And I need to outright that. So this also needs to be as a U8. Now, CPU out B, self.port.base, and buff size underscore h. Next, I do buff size low. So let buff size underscore L equals to buff size as U8, and then CPU out B, self.port.base, buff size underscore L. Next, we write the mid, which is buff size shifted left by 8. Let buff size underscore M equals to buff size shifted right by 8 as a U8. And then CPU out B, self.port.base, and buff size underscore M. Next, I do some just random write with any value, and I gotta loop that as many times as the value rewrote in step 4. Step 4 is the buff size h. So I need to do 4 whatever in 0 to buff size underscore h. I need to do this kind of CPU out B, self.port.base, and I'm going to fill it with U8 max. I'm going to write the maximum U8 value in there, which is just going to be FF really. And I need to do that as many times as the value we wrote in step 4, which is this buff size underscore H. So that's why it's in this for loop. Okay. And that's done. That initializes the device ready for an exploit. So it's really initialize device for exploit. Initialize device for exploit. And then easy port the trigger exploit that also needs to take a buff size. Now trigger exploit. Here pub create fn trigger exploit. It takes buff immutable self, takes a buff size as a U32. And how do I trigger the exploit? I need to use rep ins with the port. Okay. Inline pub fn read string from port. Uses rep ins to read a string from the provided port into the provided buffer. It takes the port and the buffer pointer. It uses rep ins b to repeatedly read from a port where it takes in out dx, port in out rdi, buff as mute pointer, in rcx buff.len. So we got the length from rcx. We have buff as mute pointer there, and that's executed here. This complains that cannot assign to this expression because it's used as an in-out RDI. Buff then. Let me do let buff start equals to buff.as mute pointer as usize. And then this should be buff underscore start. Oh wait, this should be a mutable value. Port also needs to be mutable. Let mute port equals to port. Actually, I don't need to do that. I can just do mute. Okay. This is read string from port. Rep ins b, is that the one I needed? Yes. Rep ins b. Okay. If I look at the actual rep ins b x86 instruction, I would rather actually read this from the documentation, but let's see. It's the port to read from. The data read from the port is written here. The number of bytes of data to read is the count. And it reads data from the specified port using the rep ins p instruction. That's exactly what we're doing. Providing the port and the buffer and the size. The size in RCX, the start of the buffer in RDI, and the port in DX. And it's in out, in out, in. I wonder, does INSB actually require DX and RDI to be in out? Because I wouldn't think so. Because I shouldn't actually care about them. going to be an assembly instruction that takes the port and the buff start there, and then the length there. And it's going to operate on that, read from the port, and write it into the buff start buffer. Okay. Oh, this should be fine. Read string from port. Trigger exploit is buff size, and what I need to do then to trigger it is loop reading buff size -1. So just a forever loop here. Trigger exploit should not return, and then forever loops on CPU read string from port. Well, actually, first I need to allocate a buffer, right? Let buff equals to now if I had the heap, I could do a hard-coded, a dynamic allocation, but since I'm not using the heap here, I have to hard code the allocation on the stack. So what I'm going to do is just have an assert that, well, let me do this. Const buff size equals to 10. I'm going to have an assert that buff size is the same as buff size. And this is going to be a U32. And then as long as that matches, I can then loop here, read string from port, where the port is 431. So self dot port dot get port by offset 1, right? Because 431, and the buffer is going to be a hard-coded buff here. Let mute buff equals to buff size there. So the buffer here is going to be at mute buff, and read string from port. I'm going to have it take a size, which is going to be usize, and that's going to go into RCX here as size. So the size I'm going to provide is buff.len -1. But it's mutable. Okay, it's going to be buff size -1. As usize. Okay. So it's going to loop reading from the port using the insb stuff for buff size -1. And I don't actually need the loop here because exploit itself never returns. Exploit here never returns because of trigger exploit, which never returns. Okay. This should compile. All right. Says I don't need the mute here. And it is correct. Done. It compiles. I want to open this into Binary Ninja because I just want to see what the compilation output actually looks like. D drive, terminal backup, VBox exploit, target here, debug.efi. HLIL and disassembly. Here's the EFI main. Goes to init, goes to exploit. Exploit. What does exploit look like? Initialize device for exploit, trigger exploit. Trigger exploit, fix the sizes, does a mem set, while true goes down here, gets port by offset, read string from port, which is this function, read string from port. Going to rep ins_b, pops RDI, so RDI gets saved. The caller, where's the caller? Here. Oh, well, that's fine because this function, okay, that jumps back to the start here. It moves the value into RCX, moves it into EDX, so they get overridden anyway. And this just modifies what? RCX, which gets modified anyway, DX, which gets modified anyway, RDI, which gets returned out anyway. So it's all fine. Yeah, rep ends B, we're good. All right. I should have made this inline always, because in debug builds it's not being inlined. But it doesn't matter. It really doesn't matter. It's fine. Here's our little bootloader. Cool. Seems to be as expected. Now we actually need to run this. Well, first of all, we got our little bootloader here, a little EFI file. Now we need to set up VirtualBox to actually run our bootloader and trigger the exploit, see if it works, and take it from there. So let's do that. I need to open Hyper-V Manager. I think, let me wait for this to load. Come on. I've got VirtualBox saved in here, so let me resume this VM. This is a Windows 10 VM because I think the VirtualBox version, that .16 vulnerable version, I think it doesn't run on Windows 11. It might be too old, but I don't recall exactly. I just know that I have it installed on this Windows 10 machine, so that's perfectly fine. Now we need to create the new VM. We're going to create it. I'm going to name it as exploit. Oh, sorry, did I hit the wrong button? I should hit new. This is going to be exploit, and you want the OS to be Microsoft Windows. And the reason for that is depending on what it's expecting, whether the target's Windows, Linux, Solaris, BSD, Mac, IBM, it's going to try to load the EFI bootloader file from different locations. With Microsoft Windows, it's going to load it from, I believe, EFI/boot folder. And that's what we're going to work with. So if we want it to be Microsoft Windows, I can just say it's Windows 10. Sure. Memory, we don't need much memory. I'm going to give my VM just 1 GB. Hard disk, yes, I want to create a virtual hard disk. I want the hard disk to be a VHD. Why? Because Windows has built-in PowerShell commandlets to mount and modify VHD files, and we're going to want to plant our bootloader in there. So I'm fine working with VHD. I'm going to do a fixed size just so I don't have to deal with any issues with dynamically growing the hard drive. And it doesn't need to be big. I'm going to make it maybe 1 GB, the hard drive. Okay, now there's some settings we have to do. First of all, let's see. We're going to enable EFI because we're running our bootloader as a UEFI bootloader, so EFI needs to be enabled. What else? Nothing there. Nothing there. Storage. Okay, this is using a AHCI storage. Now, the vulnerability we're targeting is a um, skizzy emulation. So we're going to add a bus logic skizzy, right? Because that's the emulation target we're fuzzing, or not fuzzing, but triggering the vulnerability in. So we need to make sure there's actually a bus logic skizzy attached to the VM. And this can just have something random in here. This can have the exploit VHD there that it points to. But for booting, we're going to boot off. We should be able to just boot off SATA here. That should be fine. I don't think VirtualBox allows you to boot off of bus logic skizzy, which is why it's not going to be the only controller here. We have a SATA controller for booting from. If this fails, there's other controllers I can use for booting, but this should be fine. And bus logic's there just to be a controller that's added. And it says that it doesn't work with the VHD, but I can have it I could have it be associated with something else. I can leave it empty. An empty disk is there. The controller's there, bus logic skizzy is there, but it's going to be an empty disk. I also add just an empty hard drive. You know what? I can create a test hard drive, which is a VHD, dynamically allocated. It's going to be like 50 megs. And that's going to be associated with this bus logic controller too. Okay. Cool. I think that's fine. I don't think there's anything else I need to do. All right. Now I need to mount the VHD. I'm trying to load that up, but it's being a bit slow and freezy. You know what? I'm just going to reset the VM. I don't know what state it was saved at. So I'm just going to reset that. Let me log in. Ah, not command prompt. I wanted. There's no terminal here. Give me PowerShell. And I want to go to C drive users, user one, VirtualBox VMs, exploit. I want to go to here. And I want to do something like, well, actually, I can open up disk management here, and I should be able to go to something like action attach VHD. And then in attach VHD here, I can find the exploit VHD, open that, and click OK. Now this, I want to format it. Initialize disk. GPD should be fine. And I need to create a new simple volume. For UEFI booting, it needs to be FAT32, I believe. So this is going to be formatted as a FAT32 exploit VHD, FAT32 format. Have that formatted. Done. Now that's mounted here. I need to create a folder called EFI. I think it's EFI boot. The EFI is the first one. And then the second level folder is boot. And then the file in here needs to be my bootloader named bootx64 .efi. So let me exit out of the VM. Let me open up my VBox exploit EFI that we compiled. Let me make sure the compilation's up to date. Yep. Copy my exploit.efi. Whoops, where'd that go? Here we are. Copy that. Open up the VM. Copy it into the EFI boot folder on the VHD. Rename it to bootx64.efi. So now under the VHD, it's got EFI, boot, bootx64.efi. Okay. Let me eject that. Done. Now let me open up VirtualBox. Yes, there's a new version, but I don't want it. Now, let me try running our exploit VM and see what happens. Hmm. Let me power off. Seems like nothing happened there. You know what? I want the VM to crash if nothing happens. So under here, where's that final loop? Trigger exploit has an infinite loop. I don't want an infinite loop. I want to do for whatever in 0 to 20,000. Do this. And then if for some reason after 20,000 reads here, it doesn't crash, then I want to crash myself by looping the UD2 assembly instruction. That way, if the exploit fails after 20,000 attempts, the VM itself will crash to indicate to me that it at least was running and got that far. Let's build it. Now let me copy the new version I just created. Go back to my VM here. Reattach that VHD. Go into it. Paste it. Update the name. Okay. Eject. All right. Now let's try that again. Okay, so let's run exploit VM again. I wonder if it's just not running. So let's try this again. Let's terminate the VM. Let me go into the settings. System. Boot order is going to be hard disk. What else? Storage. We have bus logic. Let's exploit one VHD. But I actually want... so that's not going to be for booting. Let me remove SATA. Let's create IDE for booting. Let's boot over IDE. Oh, no, I should be able to boot off SATA though. Should be fine. And it should be able to boot from exploit.vhd. This SATA port 1 maybe has to be the boot. This is SCSI port 1, which is fine. I don't want that to be the boot. I want AHCI to be the boot logic. Okay. Start. Okay, here we go. We booted into a UEFI shell. This is because VirtualBox obviously has a UEFI shell in here. We're going to FS0. At FS0, if I do ls, you see there's the EFI folder. We go there. We go into boot. And then here we see the bootx64.efi, which is us. So we can just run bootx64.efi. And that's running now our bootloader. And just let that run. And while that's running, if I look at VBox here, that should be doing out of bounds reads. I go back here. This should be triggering out of bounds reads because based on the source, right, we write to the reset port, we write to the write register here out to port 430 a bunch of times, with 0 and then with 1, and then right here just sets that to 0. Here sets it to run 1, goes down there, and then after that it's the that gets the buff size ended with 0x0f, and that has to be 16 or less, which it should be. In fact, it's probably going to be 0, so that should be fine. Ah, wait, the buff size high. This is going to be the val ended with F0 shifted left by 12. And that gets the CB buff. But this CB CDB down here on this read command, if ICDB, which is going to be incremented every single time we call this, if that is equal to CB CDB, then it goes down and does the write. CB CDB can be set to 16 if we provide 0 as the high value here. That's most likely is actually going to be 0. And then CB buff is going to be 0 and that shifted left by 12. It's going to be 0. And then the second one here, it's going to be odd equal to uval, and then odd equal to val there. So maybe what I'll do is for the VBox exploit, the buff size here is going to be U16. And trigger exploit is also going to be a U16. And now here, when it does that first value here, buff size H, it's actually just going to be 0. And it's going to write that out. And then going to do the low, and then it's going to do the high, because the low is going to be odd here. The high, it's going to shift it left by 8. We shift it right by 8. And then here, we pass the value. ICDB, since I provided 0, it's going to be 16 when it's 0. Going to do this a bunch of times, and only once it matches CB CDB is it going to go down here. So if I do it 16 times, this is 0, right? When I do it once, it's going to set it to 1. When I do it 16 on the, well, for the first time, it does it. This is going to be 0 going to 1, and now it's 1 here. So if I do it 15 times, it'll be 15. It'll be 1 before. So I should actually be doing this for 0 to 15, which will be 0 to 14, which is 15 times. And it's going to write U8 max. So it's just going to write out U8 max into here and plus there. And that's it. And then when we go to trigger exploit, buff size is 10 here. Trigger exploit is called with 10. That's fine. We go in here. It's going to create that buffer of 0 U8s of 10 there. And it's going to use insp to get port byte offset on 1. And there, Y. Oh, sorry. Hang on. Wait a moment. We go back. Here, if I go down further. Once it does the 16th one, right, the very final 16th one, it sets the state command ready, sets CB buff left to the maximum of the buffer. If it's 2 device, which it is, it goes down here, and it creates a buffer based on CB buff there, and that's it. Done. So this actually needs to be 16 times. 0 to 15. Done. You do trigger exploit, it's going to go to that read string function 431. VBox gives you read string. It's going to go down here, get to this 431. And make sure that the register offset is 1. The only register 1 can be read from a string, right? 431. Make sure that PB buff is valid. Make sure that the state is command ready. Assert that it's not busy. Goes in here. CB transfer equals to PC transfers times CB. While buff left is greater than 0. CB transfer is less than or equal to CB buff. Yep. I'm reading max minus 1 byte. I'm reading 9 bytes, right? 9 is less than 10. 9 is not greater than CB buff. So you'll skip that. We'll go down here. It's going to copy 9 from PB buff plus the offset into the dest. And then iBuff gets plussed, CB buff left gets minused. If that equals to 0, which it won't, reset, but it won't. Now when I do it again, comes back in. CB buff left is 1. Okay. Goes in here. We're reading 9, which is not greater than 10. Goes here. Copies 9 from iBuff and PB buff to there. iBuff gets incremented by 9. CB buff left gets minused by 9. CB buff left has suddenly overflowed. It doesn't equal to 0. It's overflowed. It's not going to go there. It's going to loop out. That should be correct. Oh, so actually DX is in and buff start is in out. And I think here I can just do buff start. You know what? I'll have it here as buff.asMute pointer as usize, and that can be mute. Okay. Value assigned today is never read, except it is. That's perfectly fine. It's in out. It's fine. Okay. Now that should trigger the out of bound read. Where is it? The out of bound read. Because it reads from PB buff plus something into PB dest. Maybe I'll use a larger number than just 10. Let's make buff size 20, 1, 2, 3. 20,000 on the stack. Is that a bit too big? 20,000 bytes? I think so. Let's make it 20 then. 0 U8, 20 is the buffer there. And instead of to 20,000, let's make it to 200 million. Okay. Now, where have I used 10? Instead of 10, it's 20. Any other use of 10? No. Now it's 20. It's 20. Okay, we're good. And I'm going to build it as release just so it's faster. Okay. DX is port. RDI is buff start. RCX is size. Rep ins B. Okay. Okay. We should be good. Let me copy that. Oops. D drive temp vbox exploit target release here. Let's go to the VM. Let's close this. Power off the machine. I want to. Oh, is the VHD still attached? No, it's not. It's attached one. Exploit.vhd. Go in here. Paste it. Boot x64.efi. Okay. Eject. Here. It's boot exploit. Okay. fs0. EFI. Boot x64.efi. And run that. Well, that's going. Let me take a look at vbox skizzy again. So that's happening on the reads. What happens on a write? It goes to vbox skizzy write string. Vbox skizzy write string, what does that do? If buff left is greater than 0, it gets CB transfer. Now this copies the data from the source to pbbuff plus ibuff. Ibuff gets incremented, CB buff left gets minused. So now we're doing an out of bounds write. Maybe I should combine the out of bounds read stuff with this out of bounds write, because the out of bounds write will most likely trigger the vulnerability quicker. Because in this case, if we read such that we underflow the CB buff left value to a really large value, you'll go down here, you'll see RT min, which is transfers in CB, which we're going to do a lot of them. And it's going to be CB buff left, which is going to be really high. It's going to go down here. And it's going to copy the really high value from source to the buffer plus ibuff. And it's going to increment ibuff and minus CB buff left. This is going to be a really large out of bounds write. So maybe I'll incorporate the out of bounds write to trigger the vulnerability quicker. Let's try that. Users rep out s to write a string from the provided port and buffer. To write a string from the provided buffer to the provided port of the provided size. Inline sub fn write string to port. It takes a port, a buff, and a size. Buff start is there. Rep outs b, port, buff start, and size. Okay. Now our exploit is going to do an out of bounds read. Now this is buff size is 20. And in from 0 to 16. No, this needs to be to 0 to 20 minus 1, which is going to be 0 to 19. Because if it's 0 to 1, that's already 1 time. So 0 to 19 will be 20 times. No, it will be 19 times. Okay, that means buff left is going to be, well, actually, this is going to, what I actually should do is 20 times, because now at 20 times, it's going to underflow by 1, and it's going to be a really large number. Maybe I'll make that 21 just to make it a super, super large number. Okay. Because it will underflow at that point. Because that will, if I go to skizzy read string, CB transfer is PC transfers times CB. Right, the count I'm providing in the rep command. No, the count I want to provide to the rep command needs to be less than the max. So wait, what is this 16? I'm getting confused for a moment. 0 to 16 does this right, which is initializing the device for exploit. Oh, that's because, let me go back to where that is. Because that is the right register, and this is register 0, and this is the last step here. Right, where once ICDB equals to CBCDB, then it sets the state to command ready. Okay, yes, that makes sense. Okay, so that will be 16. That's fine. And then once that's done, it gets to trigger exploit. Trigger exploit, we create the buffer. We read string from port, buff size -1. And doing that once will, actually, in trigger exploit, doing that once will get it close to an underflow. Because we're providing, if the buffer size is 20 and we're reading 19, that's fine. If we do this twice, then it's going to underflow. Once it's underflown, because we've done it twice, we can then go and do a bunch of writes. So now, for whatever in 0 to 200 million, we're going to write. And we're going to have a buffer. Let buff equals to 0xff u8, and buff size is usize. And we're going to write string to port. We're going to get port by offset, which is going to be 1. We're going to pass through the buffer, and it's going to be buff size -1. So we're going to write, instead of 20, we're going to write 19 bytes every time. And those writes should go through here, right? CB buff left will be a really high value. It's going to grab our value of 19. It's going to write 19 bytes into this location, increment iBuff, decrement CB buff left, which is just going to be super high, and it's just going to keep writing. And since it's a write, it should definitely trigger a out of bounds write or overwrite some critical structure or something pretty importantly. So this should trigger the bug. Let's compile this. That's compiled. Let's go to release VBox EFI. Here we go. Let's go to the Windows 10 VM. Let me terminate the VM. Attach the VHD. Go into the VHD. Boot x64. Actually, probably doesn't need to be named boot x64 since we're calling it via the EDK UEFI shell. Boot x64 is there for it if it was going to be auto booted into, which we're not currently doing. But it's fine. CDFI, CD boot, boot x64. Okay. Perhaps we're doing something wrong. Let me revisit what we're doing step by step. Okay, we initialize SCSI port. SCSI port, it's 430, 434 is max. We create it and we return that out. Then we call exploit. Exploit does initialize device for exploit. Initialize device for exploit calls reset. Reset writes 0 to the port out. Okay. On port 3, get port by offset. All that does is adds 3 to base, make sure it's not max and returns it, or not greater than max and returns it. Okay. Then you write 0. Then you write this value, which is 1 at base. Then you write 0 to base. Then you write the low U8 part of the buff size to base. Then you shift it right by 8, truncate it, and pass that out. And then for 0 to 16, you write this to CPU out there. Then you go to trigger exploit. Trigger exploit goes here. Creates a buffer. Reads string from port. Gets the port by offset 1. Passes through the buffer and the buff size -1. Does that. For twice, once will read right up to the second last byte, and then it does it again, and it's going to overread and underflow the buff left value. Then you get to this write. In this write, it's going to write a whole bunch of Fs to it based on the size -1, which is going to be less than buff left, and it's going to write that. It's going to decrement buff left and increment the offset, and it's just going to keep doing that a bunch of times. And that should be overwriting a lot of memory. I would expect it to trigger a crash, which I don't see, interestingly. So we're going to debug this a bit. Let's go into our EFI. Let me create a function. I'm going to have a function. Sorry. I'm going to have a function called crash. And it's just going to loop this ASM UD2 instruction. In my EFI main, I'm going to call crash. Let's see what happens when I do this. Copy it, paste it to the Windows 10 VM. We'll actually first attach the VHD. I don't need to rename it because it's not auto booting. We're just manually booting it ourselves. Let's see what happens now. I just want to get some sort of feedback to know whether code is executing properly or not. Interestingly enough, UD2 is not crashing the machine. Okay, so I had a little bug that I figured out. So first, in the CPU, the RDI here in read string from port for rep in speed is in out. I just needed to mark that buff start is the in and then have this little equal to arrow pointing to what's the output, which is going to be nothing. And I compile this as debug because I haven't actually guaranteed that in release build nothing's being optimized out. Just because in release build, if certain things don't appear to have actions and they're not marked as volatile, they can be optimized out. So I just build it as debug build. And so what the code does, right? If I main initializes the skizzy port structure there, calls exploit. Exploit calls initialize device for exploit. I made the buffer size 20. Initialize device for exploit will do the reset command, do the out B with 0, and then out B with the TX2 device. Then for the sizes, we set the first size as 0, then the low 8 bytes reset, and then the middle 8 bytes reset. And then when you do the first size as 0, in the source code, you'll see that it sets this CBCDB, if it's 0, sets it to 16. And then later, in order to get to command ready, ICDB needs to equal to that 16 value, that CBCDB. And ICDB gets incremented every single time we call into this block. So for 0 to 16, to do 16 times, we just write a random, well, it could be any value. I just do U8 max, which is FF, to here, and that'll do it 16 times, such that the very last time it does it, it'll go down this if block here, set the state to command ready, initialize cbuff left, allocate the pbbuff buffer to the 20 bytes that we're allocating, and done. Now, after that, we trigger the exploit. In trigger exploit, we do 2 ways of triggering the exploit. And we combine them for higher chance of actually triggering the exploit. The first one, we do an out-of-bound read and make the CB bytes left value be super high. How do we do that? Well, let's look at skizzy read string. We read the string and we read buff size -1, and we do that twice. So what happens is on the first time, it says, is buff left greater than 0? Yes, it's going to be that 20 bytes initially. Go down. Is what we're trying to read, which is buff size -1, which is going to be 19, is 19 greater than 20? No. So it won't go into there. It'll go into here. It'll copy 19 bytes into a buffer. It'll increment iBuff by 19, subtract CB buff left by 19. So iBuff will be 19, CB buff left will be 1, because it starts at 20, it'll be 20 minus 19, it'll be 1. When we call it the second time, it comes back. Is 1 greater than 0? Yes, comes in here. Is 19 greater than 20? No, doesn't go into here. Copies 19 bytes from pbbuff plus 19, which is a overread, into pbdest. iBuff gets plus by 19, so it'll be 19 plus 19. CB buff left, which was 1, gets minused by 19. So it underflows into a really high unsigned value, a super, super large value. That's the 2 reads. So it triggers an out-of-bound read and makes CB buff left a super, super high value. Then for 200 million loops, we write we write a string of 19 bytes. That write goes to skizzy write string function. This function will check, is CB buff left greater than 0? CB buff left is going to be that super high value. So yes. Goes down. CB transfer, the minimum, gets either CB buff left or the value we provide. We provide 19. Is 19, so it'll use 19. Then it's going to copy 19 bytes from our buffer into pbbuff plus ibuff. And ibuff is going to be that 19 plus 19, which is already out of bounds of pbbuff. And then it's going to get plus by 19 again. And we're just going to keep calling this, and we're just going to keep overriding memory in pbbuff. It's just going to keep writing memory. And since we're doing a lot of writes, it's eventually going to overwrite and corrupt some inaccessible memory or read-only memory and cause an exception. Let's try that. Compiled it as debug build, copy the debug build, EFI file, go into the VM, attach the VHD, go into the exploit VHD, paste it, eject the VHD, run the VM, fs0, EFI, boot, run, done, and it's crashed. And it tried to auto attach WinDebug to it, but it's a protected process, so it's not going to be able to debug it. But it died, it crashed. That's that. That did the exploit. That triggered the vulnerability. Just stop that. So there you have it. We wrote our own little exploit here. Well, not an exploit, but we triggered the vulnerability here ourselves in our own little mini OS. We didn't have to write a Windows kernel driver with a userland component. We didn't have to boot up a full Windows guest. We just wrote our own little code here to trigger the exploit. Well, not the exploit, but trigger the vulnerability for us. Now I'll share a slightly enhanced version of this that has capabilities to print output to the screen as it works with UEFI, just to show that off a little bit, but it'll trigger the vulnerability all the same.